So in the second part of the problem, we are asked to construct the energy momentum tensor for classical electromagnetism. So the energy momentum tensor, if we look at equation 2.17 of chapter 2, takes the following form. So that's the derivative of the Lagrangian for mu. Now, the difference with equation 215 is that we have here several fields, so we will sum over all these fields. So that's why I introduced this label sigma here, minus mu. So this is something we can construct. So the first term here, the first derivative, we've computed that in the first part of the problem. So we know that this actually gives us 4 f mu sigma, but we have this minus 1/4 factor we should not forget. So here we go, mu sigma, sigma, and the Lagrangian, then that makes f. I will write that like that, and yeah. So this is apparently not symmetric in mu and nu, but as the problem suggests, we can actually add a term which is a full derivative in order to make that symmetric in mu and nu. So the term that I suggest we had is the following. So I will call it t hat. So that's just t mu nu plus, and we add this term which is a full derivative, so with lambda, k lambda mu nu, where k lambda mu nu is actually f mu lambda a nu. So the first thing that we might check is whether this term that we had does not pose a problem for the conservation of the various charges. And in particular, we should check whether the derivative of t hat mu nu is still 0, assuming that the one of t is. So we want to check that whether this term indeed vanishes when we compute the derivative. It does. You can compute that quite easily. So first of all, you might switch the derivative order. So first lambda. So we actually first do the mu derivative, a nu. So we have here 2 terms. The first term here, lambda a nu, so that's like that, plus, now the derivative acts there, f mu lambda. So this term here vanishes, that's actually Maxwell's equation. So that was the first part of the problem, so that's 0. And the second part here, so let me write that a bit better. Okay, let's actually compute the derivative, a nu. So f mu lambda plus mu a nu lambda f mu lambda. So the second term vanishes, that's also Maxwell's equation. The first term vanishes because this operator is symmetric in lambda mu, while the tensor here is antisymmetric. So this is actually 0. So indeed, we can add such a term to the energy momentum tensor, and that does not affect the conservation of energy and momentum. Okay. So let's compute explicitly t at mu nu now. actually get rid of these parts. So, okay, so that's just what we have before. So minus F mu sigma A sigma plus 1/4 of FF, F mu nu, plus this new term here. So what we see is that when the derivative acts on F mu lambda, this will be 0 because of the equation of motion. So only the second term remains. And to make things easier, instead of calling that lambda, I will call that sigma. Okay. So the only term that remains is F mu sigma d sigma A nu. But now we see that we can factorize in the first and third term the F mu nu. That's F mu sigma. Yeah, F mu sigma, sorry. And then we have here, so let's write it explicitly, minus nu A sigma. That's 1/4 F mu nu. And that's actually the definition of F sigma nu. Okay, so we have now the expression of T at mu nu, which is now clearly symmetric with respect to mu and nu. So what we can compute from that is, are the different charges, conserved charges. So the charge which is conserved with respect to time translation, the local one is the 0,0 component. It's actually the local Hamiltonian, and we can just compute that. That's F0 sigma F sigma 0 plus 1/4 of FF. Because delta 0,0 is 1. So we have two terms here. We recognize in the first term the electric field. Okay, so let's remind us that EI is equal to minus F0I. So clearly here in the first term, sigma can only take spatial components, so 1, 2, 3. So I mean, if you want to make it easier, okay. 0I F. I will already invert things, so 0I, that comes with a minus sign because it's antisymmetric, plus 1/4 of FF. Now, the spatial components here, if we want to express it in terms of I on top, it takes another minus sign, so it's actually F0I in the end. And that's therefore just E, scalar E. So we just need to compute FF. So 1/4 of FF is equal to 1/4 of, so let's just write it, F mu nu, F mu nu. Now, mu and nu can take value 0, or let's say I or G for mu and nu. So we have the sum of F0. So when mu is equal to 0, nu can only be spatial component, so that's the J I mentioned, so J. Oppositely, when nu is equal to 0, mu can only take the value I, let's say, so 1, 2, 3. And then we have the mixed case, Ij, F, Ij. So let's compute that. So that's 1/4. Now, if I only use top indexes, So the first term will get a minus sign because the zero component does not get a minus sign, but the other one does, according to the convention used in the textbook. And we have here, and the same here, so that's f I f0. And what we have here, as you see, is two, so let me just write fully top indexes. So the first two terms are actually equal, so that's minus 2 f o j, let's say, f o j. And the second term is just a scalar product of magnetic fields, as we've seen before. So I can write that I j L I j k B L B k. Okay, so the first term here we recognize two electric fields, so that's 1/4 of minus 2 E scalar E. And what we have here, so this is the scalar product of B, and it's actually 2 times the scalar product of B times B, because, I mean, as we can see, L and K have to have the same value, and for a given value of L, we have I and J and I, which gives the same value because we have here a product of the same epsilon tensors. So there's a factor 2 coming out. And that's the result. So that's, in the end, I can extract, so that's 1/2 of B minus E squared. So in total, you remember that here we had already this factor here of E scalar E. So the conserved charge with respect to time translation is therefore 1/2 of B plus E, which is indeed the classical result that we know from first lecture of electromagnetism. Okay. We can now compute T at of 0I. So that's F0 sigma F sigma I plus, well, actually, so 1/4 of FF delta 0I, which is equal to 0. So we only have the first term. So sigma, as you see, can only take special values because the first term would be 0 otherwise. So that's F0J, Fji. So we can manipulate that a bit. So that's F0J minus Fji. And we have, so the first term is minus Ej, and the second term is epsilon Ja L B L from the definition that we've seen before. And that is simply, let's write it this way, JILEJBL. If we want to make clear what it is, so we can just write JLIGBL. And that is the ith component of the cross product of E and B. So that's T0I as a vector, let's say, is what we call in classical mechanics, so electromagnetism, the Poynting vector.